Hey guys, welcome to GeeklyEDU Chemistry. My name is Sona Singh and today we will talk about the Arrhenius equation. A quick recap is necessary here that in the last video we talked about how the rate of the reaction can be influenced by several factors. For example, the initial rate of the reactants. We also said that the rate depends upon the collisions. We said there should be number of collisions, there should be the quality of these collisions. For example, we said they should be happening in proper orientation. We also said they should carry an energy, and we defined this as EA, or the activation energy. And also we said that all of these factors, the collisions, the orientation, the EA, can be influenced by temperature, right? And today, the Arrhenius equation is going to explain how temperature can influence all of these factors and how we can use this to solve a variety of problems. But first, let's try to look at some problems that we should be able to solve with the help of Arrhenius equation, right? So let's get on to it. Now here in this picture, you can see three graphs, right? They have different EAs. As you can see, the difference in the original energy of the reactants and the final energy of the transition state, right? So if I ask arrange the rate forward constants from smallest to largest, you should be able to estimate which one should have a high or a low rate constant, assuming that the number of collisions, which is also temperature dependent, and we will see what happens to that, does not change. Also, we should be able to look at a variety of data and make estimates. For example, here you have data from temperature and K, right? Now, we should be able to calculate the activation energy or estimate the value of K at some another temperature as well, right? Arrhenius equation is going to help us do exactly this. Okay, so let's get right onto it. Now imagine a graph here, and on the x-axis we are plotting the kinetic energy of the molecules which are entering the chemical reaction, and on the y-axis we have the fraction of molecules that have a particular kind of energy. So what happens as you increase the temperature? The blue line shows the fraction of molecules where at particular energies, and the red line shows the same at a higher temperature. Now, if we say a particular energy to be an EA, the activation energy, we can clearly see that the amount of molecules, the fraction of molecules who bear this EA is larger in case of the red line or at higher temperature. And this makes sense because when you increase the temperature of any gas, you have more kinetic energy of the molecules, right? And that is why the temperature can influence the EA and as well as the collisions. We should keep this in mind. Now, if we want to find out what is the fraction of molecules that bear the energy equal to EA or higher, then we'll use the equation F is equal to E to the power minus EA upon RT, where R equals the gas constant and T is the absolute temperature. So F gives you the rough estimate of the fair number of or effective collisions that is going to happen. And obviously that is going to affect the rate constant. I hope you remember that. If you don't, there's a separate video for that. So we can safely assume that if temperature increases of a particular system, then EA upon RT is going to decrease. Why? You have increased the temperature, right? And we can come up with a relation on how rate constant depends. So that is K equals A E to the power E A minus RT. Now, A is a frequency factor. Now, we should remember a point that obviously this frequency factor is liable to change, right? But the change is very less compared in magnitude compared to the exponential factor. That is why we near about keep it the same, and we think that it does not affect us. Now, since EA upon RT changes, that means minus EA upon RT increases, right? And that means E upon EART will also increase, and that means the rate constant increases, and we can safely say the reaction speeds up. Okay, now how does this changes things? We'll study about this, but now this equation that you have is the Arrhenius equation. Now, this was given by Svante Arrhenius, but remember guys, I haven't added the log. So you can simply add log to both sides, and this can be used to solve questions. Now look at this question once again. So we can clearly see how the EA is in the three cases. if we number them 1, 2, 3, we can quickly arrange EA 2, that is 25 is greater than 3, that is 20 is greater than 1, which is just 15. So EA goes up, right? So minus EA upon RT is going to go in the opposite direction, right? So 2 is less than 3 is less than 1. And so will decrease E upon minus EA upon RT, right? So same trend 2, 3, 1. And finally, K will follow the same trend 2, 3, 1. So we can quickly arrange that the rate constant, specific rate constant is in that ratio. Now let us look at another problem which we also said would be able to solve using this. Now I'm going to hit pause here. You should hit pause as well and try to solve this yourself. And the hint is right there. Remember, you can add log to both sides. So if the Arrhenius equation is K equals AE minus EA upon RT, just add log to both sides and see if you would be able to come up with an idea as how to solve this. Okay, I really hope that you tried your best to solve this one. Now, if you apply the linear equation y equals mxc to the the log form, so you can clearly see if you plot the log of k on the y-axis and x, that is 1 upon t, on the x-axis, which can be quickly obtained from the table, you can form minus a upon r as a slope and c as the intercept. Now, remember, it should be in Kelvin. So I'm quickly going to write the values, and I am very sure you must have as well. So going ahead, if we quickly write all the values for 1 upon T, and remember this is after converting that into Kelvin, that original temperature was given in degrees Celsius, right? And we calculate ln K as well. We can quickly plot the graph. For here, obviously it won't be up to scale. So for representative purposes, I will be drawing this line. Now, once you have the graph, you can quickly calculate the slope by using the tan theta or simply 2 points y2 minus y1 upon x2 minus x1, right? So we calculate that from our graph to be 1.9 into 10 to the power 4. Okay, now very important thing that you must remember here, that our question was asking about EA. So just take it the opposite side and do the calculation, and you'll get something around 1.9 into 10 to the power minus 4 into 8.314, which is the value of R. Do the maths, and you have 1.6 into 10 to the power 2 kilojoule per mole. Okay, so first part of problem, the activation energy is solved. The second part of problem is the value of K, which we are going to solve now. But I again want you to hit the pause and try to do this on yourself. I hope you did that. Now, the idea is very simple. If you see, you can just write the equation for two different temperatures, right? So ln K1, ln K2, T1, T2, and subtract both the equations, right? So you simply have ln K1 upon K2 equals EA upon R 1 upon T2 minus T1, right? Now, you have 3 out of the 4 quantities, and you already calculated EA, right? So what the question is asking is that at temperature, that is 430, K1 at T1, you have been asked to find, that is 430 Kelvin, and K2 is already given in the table, that is 2.52 into 10 to the power minus 5, and add that, what is T2? 462.9, right? Now, what you simply will do is use the equation. So you'll apply the maths, plug in the values of K2, EA that you already found. It's 160 because it was 1.6 into 10 to the power 2, right? So you can simply write it 160 kilojoule. Okay, now please be very careful with the units here because it's kilojoule there. The value of R is in always joules, right? So you'll simply do the maths here, and you'll find out that the final value that you want to find out of K1 comes out to be around 1.0 into 10 to the power minus 6 per second, right? Again, be careful with the units especially. Now guys, here's a homework problem that I want you to solve. Okay, so I'm gonna hit the pause so that you can take a screenshot of the same, and it will help you to solve this, and I will leave the answer down to the same problem that I'm mentioning down in the comments. So this is a problem, value of K for a reaction at 0 degrees given, and you have to find out the activation energy is already given, the value of K at 2.0. So use the same equation.
We hope you like this video. Press subscribe, thumbs up, and stay geekly.